check if a given pair of vectors is perpendicular, pair of vectors in R3. Someone say that again? Huh? I'm one of those people who call your bluff, so I want a hand up and I want an answer confidently. Yes, sir. Yeah. What in particular about the dot product? If it equals 0, then they're orthogonal or perpendicular, exactly. So presumably we all know how to compute dot products. You take the sum of the products of the corresponding entries. And in this case, if I didn't do my arithmetic wrong, only C has a perpendicular pair. Does anyone disagree with that? Arithmetic is not my strong suit, but I believe only C is perpendicular. Yes, sir. You got B is perpendicular? Let's do that. See, this is the one that I was unsure of because I can't do math. Oh no, sorry, B. That's the one I meant. That's the one I meant. Yeah. B, thank you. That's what I wrote down. Good. That's straightforward enough, I hope. I'm going to try to go reasonably quickly through these multiple choice things because I imagine people will have more questions about the Epsilon-Delta stuff at the end, so let's try to go reasonably quickly through this. The next question asks, which of these following four matrices is invertible, is not invertible, if any? So there's at least two ways of checking if a matrix is invertible or not that I can think of. Three ways I can think of off the top of my head. Can someone give me some of those ways? I'll take a different person with respect. Yes? If the determinant is not 0, then it is invertible. Good, so you can check if, you can compute the determinants of all three of these matrices. And if you get any zeros, then it's invertible. Can anyone give me another way? There's two more ways, which are very similar, that I know. Yes, sir? It can be row reduced. Can you be a little more specific? Yes, if a matrix can be row reduced to the identity matrix, then it's invertible. There's a lot of talking going on. If you don't want to listen to me, you don't need to be here. So let's everyone pay attention or don't be here, please. Thank you. There's no need to come here and not pay attention. It's a waste of both of our times. Thank you. So yes, one other way is, so that's four ways now because that wasn't one of the ways I was thinking. So you can compute the determinant. If it's 0, then it's not invertible. You can row reduce it, and if it row reduces the identity, then it is invertible. Any other ways? There's two more ways I can think of. The ways which I think are easiest or fastest. So the ways I'm thinking of is that if your matrix has a linear dependence among its columns, then it's not invertible. Or if it has a linear dependence among its rows, then it's also not invertible. So that condition is a sort of a subclass of the condition that you mentioned about row reduction, but it's easier to check. So the first thing that jumped out at me when I saw this question is that in matrix in matrix A rather, the sum of the first two rows is the third row. So matrix A is definitely not invertible. Also, matrices C and D definitely are invertible, and it's very easy to check without computing anything, because it's pretty easy to see that you can that the rows of those two matrices C and D are linearly independent. So A is not invertible, C and D both are, and then B also happens to be invertible. You can check that any way you want. So in this case, the answer is A and only A. So the takeaway here is that you can check the determinant, or you can check to see if there's a linear dependence among the rows or among the columns, or you can just row reduce it, whatever you like. I like the checking for linear dependence just because it's faster for me. So this question asks, which of the following vectors is normal to the tangent plane of this graph, or this curve that's described by the equation z is equal to x squared plus y squared. So how might you approach this? Just give me a brief idea of the answer here, of how to approach it. What in general is a way of finding a vector that's perpendicular to a curve like this? Yes, seeing no other volunteers, I'll take you. Of? So the gradients are certainly involved. So if you have a function, its gradient is perpendicular to something. What is perpendicular to what? I'll take an answer from someone other than these two people, if that's okay. Yes, sir. Sorry? The gradient of what, though, is the question I'm asking here. So the gradient of the curve x, like the gradient of just the x squared plus y squared will have two coordinates, right? So it's kind of not, like it can't be equal to any of those three coordinate things. Do you see? So that's not quite what I want. Yeah? Exactly. So the gradient of a function, the gradient, let me say something like gradient of g is a function. So let's say g is a function from R3 to R. Then the gradient of g is perpendicular to the level sets of g. The level sets being the sets on which g has a constant value. So when you're trying to find a vector that's perpendicular to a given curve, the first thing you always want to do is express that curve as the level set of something. So in this case, this curve, z is equal to x squared plus y squared, is a level set of g of x, y, z equals x squared plus y squared minus z. So one vector that's perpendicular to this curve is the gradient of that function g at that point. And so if you take a moment to compute it, my computation, which could easily be wrong because I'm very bad at arithmetic, is that the gradient of that function at the point, man, this room is too large. I can't do anything here. Gradient of this function at this point turned out to be this. Someone scream at me if that's wrong, but that's what I computed. Two x. See? There you go. That's right. 2, 4, minus 1. Yep. So what the question is asking basically is, are any of those vectors parallel to this vector? And the answer to that appears to be yes. C and only C. The answer here being only C. A lot of arithmetic errors in my work. This question seems about as straightforward as it can be. It's just asking you to compute the gradients of these four functions and plug in these numbers. Does anyone have any questions about how you might approach this problem? I can't think of if you know what a gradient is, I can't really think of a way to not do this, unless you're making an arithmetic error, which is guaranteed what I would have done in your position. But by my computations, none of them have this gradient. Does anyone disagree? Strongly? I'm pretty sure it's none. So all we're doing there is simply computing these four gradients, plugging in this one vector, and seeing what you get. One of them you get 2, 6, 4, but none of them you get 2, 4, 6, as far as I can tell. I don't see anything to explain there beyond compute the gradients. So let's move on. This is a cute question. So This definition of a function being k-homogeneous is actually pretty important to a lot of math, so it's nice to see it here. Its definition is straightforward enough that you don't really need to know much complicated stuff to understand it. So let's talk about A. Tell me about the function in A. Is it 2 homogeneous? Is it anything else homogeneous? So the question, so functions, remember, a function's 2 homogeneous if whenever you multiply both x and y by some number, the result is that number squared times the result it would have been had you not multiplied. So for function A, we can see that if we multiply x and y both by some number lambda, what you get is lambda cubed times what it would have been without the lambda, right? So function A is 3 homogeneous, but it's not 2 homogeneous, so it doesn't fit what we want. So knowing this, all you really want to check here is the following thing. Check for any lambda, is it true that f of lambda x lambda y equals lambda squared fxy? That's what the function's that's what the question's asking you. Is this true? So understanding that definition, this boils to just checking 4 things. You could, like, just computing them. So to my eyes, D is the only one that's 2 homogeneous. A is 3 homogeneous, B is not homogeneous of any kind, C is not homogeneous of any kind. What you actually get is sort of 1 over lambda squared times f of xy. Or I guess that's like -2 homogeneous, that's not really a thing we define. And D is 2 homogeneous. So here's only D. Can I elaborate on that or clarify anything about that question? New definitions can be tricky to work with, but ultimately that one's just a matter of computing things once you understand the definitions. This is a tricky question, to my mind. So here are some functions with some letters. This is a very confusing question. So the question asks, which of these is a valid application of the chain rule? So I guess you know what the chain rule says. The chain rule says that if you want to, if f is a function of ABC and each of ABC are functions of other things, then in order to compute the derivative of f with respect to one of those other things, you compute the derivative of f with respect to each of ABC and then multiply by their corresponding derivatives. So in general, for example, the chain rule would say something like this. In general, the chain rule would say something like, if you want to compute the derivative of f with respect to x, let's say, you would compute its derivative with respect to a, and then compute the derivative of a with respect to x. And then do that for all of a, b, and c and sum them up. So this is what the chain rule would say. And it would say the same thing for y, but with y's in place of the x's, as you'd imagine. So the question here is basically, are any of these correct? So for example, the first one is not a correct application of chain rule. It does the first term, because remember a is g here. In our case, this guy's g, this guy's h, and this guy's k, a, b, c. So the first a up there is just this part. And it ignores the rest of it. And in particular, it ignores b. So b is a function of x. So if you're trying to figure out how f varies with respect to x, you need to take into account what b is doing, and so a doesn't do that. So a is out for sure. Can anyone tell me which other ones are out or in? Good or bad? To my eyes, there's only one of them that's correct. So what about b? Do you think b is correct, and if not, why? I see a lot of head shaking. Someone explain, please. Look, I don't know you. I'm not embarrassed by standing here in silence. I'll call your bluff. Yeah.
Missing the term with G in it. G also has Y.
Yeah, exactly. So B is asking how does F vary with Y, and both of A and C vary with Y, and C doesn't have either of those, right? So B is definitely out. Answer B is definitely out. Answer C, what about answer C? This is a sort of slightly trickier one. I mean, it's for a different reason. Yes, sir?
Is it out?
It is out.
Because the derivative of FA, like EFTA, the next term is DBT.
Yeah, exactly. Exactly. So the second term after the equal sign in part C is the derivative of F with respect to A times the derivative of B with respect to Y, and that just has nothing to do with the chain rule. Like there's no... That has, like, I don't have anything to explain about it. That isn't how the chain rule works, so that's not how you do it. And then the last one is in by process of elimination. You might initially object to the fact that there's no derivative of F with respect to C there. You're right. So what you'd expect from the chain rule is this, right? This full thing. Or if you wanted to use the names of the functions that are in the question, it would look something like this. So you might object to this term not being there. Strictly speaking, maybe it should be written there, but in this case, since k, the function k doesn't depend on x, dk by dx is 0, and so this term is just 0 anyway. So it doesn't need to be there. So D works and none of the other ones do. Oh, this question's great. Whoa, now, hello, come back. These two questions are great. So this question simply asks which of these things matches which of these functions has a contour plot that looks like this. So the contour plot of a function is essentially a map of its level sets. It's a diagram of its level sets. So you can't draw all the level sets on one picture, obviously. So when you look at this sort of thing, you should interpret that the black lines are all level sets of the function. So which of these functions have these guys as level sets? So to think about something like, so the way I would approach this question is to look at each of the functions and imagine what their levels, or draw, if you must, what their level sets look like, and then see which one matches the picture. And to do that, you would say, well, what would happen if, for example, for part C, what would happen if absolute value of x times absolute value of y was 1, let's say, a constant, and then draw that picture. So we can do that without too much difficulty. I'm going to start from the bottom. So this is question 7. And function D, let's imagine the level set f of xy, which equals this, equals 1. Well, that's a circle, right? So and as the 1 changes, you'll have bigger and smaller circles. So the contour plot of that thing is going to look like a bunch of concentric circles, and in particular, nothing like this thing of diamonds. Similarly, for C, you might imagine this guy. This guy you may find hard to imagine because of the absolute values, but a good way to start is just to forget the absolute values and see what it looks like for positive x's and y's. For positive x's and y's, this thing looks like a hyperbola, right? It looks like 1 over x, basically. So for positive x's and y's, it's this curve. And then as you allow for x or y to be negative, you just get all the reflections of this curve. So the level, this is slightly crappy drawing, I'm sorry. But the level sets of this function will look like this. Closer to the axes or farther away from the axes, depending on the constant. And in particular, nothing like that picture, so that's out. B works. So imagine if this is a constant. This isn't something that you can, I mean, maybe you can imagine it by, again, just forgetting about these signs, forgetting about the absolute values, rather. So if you forget about the absolute values and assume they're both positive for the first part, then this is y is equal to 1 minus x, which is a straight line like this that joins the points that are a distance 1 apart. And then it's not too hard to see that it continues like this. This isn't the only way to imagine this curve, but it's one that seems easy to me. And so the various level sets of this thing will look like bigger or smaller diamonds, and in particular exactly like that picture. So C definitely works. And then now that we have some idea what we're doing, A looks quite a lot like that picture, except perpendicular and parallel to the axes rather than a diamond. It looks like a bunch of concentric squares rather than a bunch of concentric diamonds. So C is out, or excuse me, A is out. A, the level sets look like squares. And so this is the only one. This is a strictly simpler version of the same problem, essentially. In the previous one, you had to imagine 4 plots and figure out which one it was. In this one, you only have to imagine 1 and see which picture it is, right? So again, to imagine a level set of this function, you can, for example, imagine the function or the graph of the equation x squared minus y squared equals 1, which is a hyperbola parallel to the x. So imagine x squared minus y squared equals 1. What does that look like? That looks like this. Is that a graph whose picture people immediately know? I'm not actually sure about that. For me, that's just, I just know what that graph looks like the same way I know what the graph of a circle is. It's a standard graph in my mind. I don't know if that is for you. If not, if not, the other easiest way to imagine this is to imagine the level set at 0. Even just imagining the level set at 0 will solve this problem for you. So this one looks like this. And if instead we imagine this, then this rearranges to x squared equals y squared, and that's true if and only if their absolute values are the same, right? Plus or minus the square root of the square and so on. And so this is not hard at all to convince yourself, just looks like this. Looks like an X. And so once you've decided that, that pretty much eliminates all of them, except the last one, which is not remotely close to being the right one. So can someone who did this explain how they thought of it? I'm thinking of this in a way that I would think of it, but I'm not sure how you guys would approach it. Yeah.
For example, I did this thing where you let in 4 different values.
Sure.
And then I rearranged for y, and then I knew that was a square root graph.
Oh, sure. Yeah. Perfect. Sure. So that's like a simpler version of this. So if you don't have this graph in your mind, immediately, then you can rearrange that. So if you're trying to imagine the level set at 1, we said that looks like this, right? That looks like this. So if you can't just go from this to this picture immediately, then rearrange it to go here. That's what you're talking about, right? And then this thing you should be able to picture pretty easily. So that's another way to do this. That, by the way, being this and this, the two halves of it. Okay. You've got to call me on this stuff. I realized as I was pointing at that picture that this graph isn't that. There we go. That's much easier. That's what it is. Okay. Let's see. At this point, I think I really want to get to the ends, the epsilon delta part. So let's talk about this one, because while I haven't taught this course before, I've taught other multivariate calculus courses, and multivariable Taylor series. Whoa now. Why? Why? Nice. Yeah, well, I have taught other multivariable calculus courses, and multivariable Taylor series scare the hell out of people. So, what's the sort of general form of this coefficient? Like, to do this, you need to know what, in principle, this coefficient looks like, and then compute the particular derivatives and things that are required. So, what's the general form of this coefficient, let's say? The coefficient in front of x squared y. No one has any idea? Who got this question? I guess you don't know if you don't know the right answer. Well, I mean, you should know if you did it. So in general, the coefficient in front of a given monomial. So let's go to question, which one's this? 9? Yeah. One question I should ask before I start writing anything that you don't understand. Do you guys know multi-index notation? Like with alphas? Well, you do. Oh, well, that's easy then. So the x squared y term is the x to the alpha term where alpha is 2, 1, right? 2 copies of x, 1 copy of y. So, or excuse me, do you guys use this notation? Or just this? That's how I think of it, but that might be confusing because there's x's, I don't know. So anyway, the coefficient in front of this term will be this, right? It'll be 1 over the length of alpha factorial, I think is how it goes, which is just the sum of the entries in alpha, times this. So I don't know how familiar you guys are with multi-index notation. So, but I do know that multi-index notation terrifies people. So I'm aware that in writing this I may be losing some people, but for the moment at least let's do this, and then I'll decompress the notation a little bit to understand. So in principle the coefficient is this, like the x to the alpha term in the Taylor series is this. So the Taylor series will have a bunch of stuff up to here, and then it'll continue for higher indices and lower indices over here. So the length of alpha in this case is simply 2 plus 1. That's like the total degree. It's the total exponent. In this case 3, because there's 3 variables here, x, and y. So this guy is 1 over 3 factorial. And this thing in this case is the third derivative of f with respect to the first variable this many times and the second variable that many times. So it's this. And then evaluated, of course, at the point. This is all evaluated at whatever the point is. 0, 0, of course. So to compute this, you need to compute this value, this derivative of the function, plug in 0, 0, and then divide it by 6, which is 3 factorial. Yes? Oh, right, that's how that works. Yeah, sorry. Yeah. Sorry, you're right. I forgot that they're multiplied and not added. Thank you. So it's just this. That's the notation, right? Yeah. Sorry, it's been a couple years. Good. So all you have to do is compute this and evaluate it at 0. Once you get to that stage, things are pretty easy because differentiating this function is very straightforward because it's an exponential, right? So if you differentiate that twice with respect to x, you get 4 in front of it. And if you differentiate that once more with respect to y, you get a negative sign. So in this case, this derivative equals negative 4 times the original function And so when evaluated at 0, at the origin, you get -4. So the total coefficient here is going to be this -4 divided by this 2 factorial. So the answer is 1/2 factorial times 1 factorial times -4, which is -2. Is that one of them? No. So I guess the answer in this case is none. I don't fully understand why they make people learn multivariate Taylor series in second year, but because it's really not much fun at all. But that's how it is. So this is the sort of question where if you remember how multivariate Taylor series work, this is just blind computation and nothing else really. And if you don't, you kind of have no shot of figuring it out as far as I can tell. There's nothing you could do that'll help you if you don't remember how to do it. This one I think I'm going to skip for now in the interest of time. So let's brief. So the thing I want to talk about, at least for some amount of time, is this. Because I imagine, would people agree that this was the trickiest thing? Usually, by far, the most tricky thing for people is Epsilon-Delta stuff. Are you guys coming, like, this is a second year calculus course here, right? In the first year calculus course that you guys took before this, did you do Epsilon-Delta proofs for limits? Oh, you did. Okay, so maybe that's not that bad. Let's just see. Who, like, definitely wants me to go over this? There's a bunch of ways to do this. I mean, there's one way that's substantially easier, which is what I'll explain to you, I imagine, but. Okay, so let's briefly mention some of these things, because I think a lot of these computation questions are probably easier than the multiple choice ones. So this question is just asking you to find the gradient of a function, and it gives you the function. So I hope you all know how to compute partial derivatives, and if you do, there's nothing to screw up here. You can check your answer on Wolfram Alpha if you'd like. Nothing to say there. This guy is just asking you to do the chain rule. So the chain rule is this. Do the chain rule and plug in that value. I believe the answer you get should be 2. The answer I got is 2. But again, if you know the chain rule, I don't see an issue here. I don't see a stumbling block or a block of understanding here. So I'm going to leave this for the moment. 2 is the answer. Finding the second order Taylor polynomial of this thing is interesting. So the second order Taylor polynomial in general at, what is it? It's at 0, 0. So in general, that's going to look like this. It's going to have exactly this form. It's going to be f at 0, that's the degree 0 term, plus the derivative with respect to x at 0 times x, plus the derivative with respect to y at 0 times y, and then it'll have the 3 second order terms here. So it'll be the derivative with respect to x twice at 0 times x squared divided by 2, plus the derivative with respect to both x and y at 0 times xy not divided by 2, because the index, the multi-index here is 1, 1, plus the term that matches this. So the derivative with respect to y twice evaluated at 0, 0 times y squared divided by 2. So this is the general form of the answer. But one thing you can immediately see is that all 3 of these are going to be 0 without any work, really. Because if you differentiate that function twice with respect to anything, you're going to get a sign of some stuff. Like the sine x minus y will be there, and it'll possibly have some stuff multiplying it. In this case, it'll have a -1 maybe. So all the second derivatives of this thing are just going to be 0. So the second order Taylor polynomial will have degree 1. Will in fact just be a monomial as far as I can tell. It'll just be x minus y. So in this case, that I believe that just equals this. This is a very fast computation that I did on paper a minute ago. But also notice that f at the origin is also 0, as you can easily see. So this looks like more work than it is. This strikes me as the easiest question on this test. If you know about equations of planes, can someone describe how to do this? Yeah. Yeah, so that plane is given to you in standard form. So the normal is just in the equation, right? The normal vector is the vector with entries that are the coefficients of x, y, and z there, respectively. So a normal vector to this plane is simply 3 comma minus 1 comma minus 2. So knowing that, you're looking for a line that's parallel to that vector, because that vector is perpendicular to the plane, and which goes through this given point. So you don't, it's just t times the normal vector plus the point, and there's nothing to do. It's a surprisingly simple question. This one I don't want to do. Do I want to do this? Yeah, so can someone, I mean, I think we kind of already answered this, but can someone describe in general how you would start to solve this question? How do you find a vector that's perpendicular to this curve? There was a multiple choice question that was along these lines anyway, so we're kind of repeating ourselves, but yes. Exactly. So, but again, just to be super clear, when we say the gradient of that curve, we mean the gradient of the function that that curve is a level set of, right? So that curve is the level set of the function x cubed plus xy plus y cubed. It's a level set at 11. So the gradient of that function is perpendicular to its level set everywhere. So at that particular, all you have to do is compute the gradient of that function and plug in 1, 2, and you'll get a vector that's perpendicular. An idea that we've already seen in one of the multiple choice questions anyway. I don't think there's anything to explain about this question. This question is pretty much just asking you to compute some derivatives and notice that they satisfy this equation. If you can differentiate stuff, I'm not sure what the issue here could be, so let's move past it. Aha, so here's the interesting one. So this is a tricky question. It took me a minute to think about before I realized I didn't have to think very hard. So I think this question can look impossibly difficult if you don't see some maneuver for getting through. And if you do see that maneuver, it's very simple. So it's a little bit of a weird question. But the fact which I think is key to understanding this is the following thing. So first of all, let's be clear about what we want to do. We want, I'm just going to rewrite part of that question. I want a delta positive such that if this number is less than delta, note that this number is always positive, or 0, I guess. If this number is less than delta, then this giant quantity is less than 10 to the minus 4. Did I get that right? Yeah. So the only way to approach this sort of thing in general is to manipulate this expression in the absolute values in such a way that you can bound it above by something that only involves these guys, right? What you want to eventually do is take this thing, take that, manipulate it in some way to eventually get that it's less than some expression Usually, the ideal situation is to get down to something like this. This is the ideal. If you can get down to that, then you'll win. Sorry, I'm just remembering something. Is that a squared? Yeah, it's a squared. So this would be good, this would be good. If you can get to any of these places through some manipulation, showing that this thing is less than that is ideally what you want, and then you can choose delta to be this quantity over d, and then it'll work. So what's an idea for doing this? I only see one obvious method here to me, but I'm curious if anyone saw anything particularly weird or novel or. What sorts of what manipulations are helpful? Can someone say something which is useful to start with? Yes, sir. The triangle inequality is certainly a good first move because this thing is nice. This thing isn't so nice, but maybe we can deal with that later. So let me do the triangle inequality. Do the triangle inequality. So, well, I'll just write it again. So, one thing we can say because of the triangle inequality is this, and I'll see if that's what you wanted me to do or more. This guy is, let me keep going here, is less than or equal to this. So the triangle inequality tells me this. Did you want me to go farther here? Huh? Like I can do the triangle inequality again on this or on this. All of it? Sure. So this guy's not going anywhere. These guys are just positive anyway, so. And then I can say this. So this is the best the triangle inequality can do for you. So that's triangle inequality exploited and the farthest it could go. Now what? Now is sort of what to my mind is the key insight here. So what's the key insight? Yeah. X and y are less than delta, exactly. I mean, I don't really know anything about delta yet. I haven't assumed anything. But what I can say is that the absolute value of x equals this, by definition, and that's always less than or equal to this, which is what will eventually be less than delta. So similarly, the absolute value of y is less than this for the same reason. So that's good. So I can say that now that I'm just summing things, so I can just say this term and this term and this term and this term are all less than that. And this is that squared already. So this insight will get me to here. This will be strictly less. Strictly less? No. Less than or equal to 5 times this squared plus 10 times this here. So that gets me here. Good. Now what? So that's key insight number one, is that those inequalities on the right side of that board. Key insight number two is what I need now, at least to do this in the way that I'm imagining. What's screwing us up here? Like what's not allowing me to just get to here immediately? I can say that, but that's exactly the useful thing. So the problem here is that this guy, this term, this thing squared, and this thing to the 6 aren't naturally compatible with each other. I can't add them up. So what it feels like you want to say is that, well, this quantity is less than this quantity because this one has a higher exponent. So I can say that they're all less than 15 times this to the 6. But that isn't always true, right? Whether or not the 6th power of a number can be bigger or smaller than the number depending on the number, right? If this quantity is bigger than 1, then this guy's smaller than the other one. And if it's less than 1, it's bigger. So that's exactly the problem. So we need to fix that. Yes? Pardon me? Can I pick a minimum of the 2? Yeah, I can do that, but remember that ultimately what I get control over in this problem is delta, right? I can make delta as small as I want, and then eventually I'm going to assume that this guy's smaller than delta. So if I force this guy to be smaller than 1, then all of a sudden I understand the situation, right? The problem is that if this guy's bigger than 1 or less than 1, this inequality acts differently. And so if I just force it to be always less than 1, I can figure out exactly how it acts. So if, I realize I'm slightly over time, but I want to finish this point. If this quantity that I'm working with here is less than 1, then this is less than that. Because if you take a number that's less than 1 and raise it to a power, it goes down, right? In fact, even I can say this, right? If it's less than 1, then this quantity squared is less than itself. So let's do that. So continuing this chain of inequalities from here, this is if this quantity that I'm working with is less than 1, we get that that guy is less than 5 times it plus 10 times it, which is 15 times it. So having gotten here, all I need to do is make this guy less than 10 to the minus 4 over 15, and it'll work. So from here, what I want is that this quantity that I'm working with is less than 10 to the minus 4 over 15. Because if that's true, I will ultimately have proved that that giant quantity at the beginning is less than 10 to the minus 4. So ultimately, the delta that will work is the minimum of 1 and that. That's what you choose. It's possible there are other routes through this, but I think that's the simplest one. And I'm already 5 minutes over time. Sorry about that, but I wanted to finish the point. Thank you. That's all we got. If you have any specific questions about anything I've talked about or this test, because I've now solved it all, I know how to do it, you're welcome to come talk to me. I'll be here for a few minutes at least.